let's find the half-life of a compound that decays at a daily rate of 1.25%. Now, one way to solve this problem, and the way I'm going to solve it, is to model an amount of this compound decaying over time. So I'm going to write a model. A of t equals a sub 0 times 1 plus r to the t, where t is in days, since I have the daily decay rate. Now I don't have an amount, but half-life is independent of starting amount. Half-life is that number, is that time, such that any amount will be halved in that period of time. So I can start with, how about the simplest possible, a sub 0 equals 1 unit. I don't even have a unit here, it doesn't matter, just 1 unit. How long will it take for that 1 unit to drop to half a unit? So with the model, it would look like 1 times 1 plus, what's the growth rate? Well, it's negative 0.0125, and then that's raised to the t. That's getting a little muddy there. Let me clean this up. We already got those values. So raised to the t. That's my model. The positive 1.25% is the decay rate, the daily decay rate. That means the daily growth rate is negative 1.25%, which is equal to negative 0.0125 as a pure decimal. So this is what my model will look like, and I want to know when will that model give me half a unit as a target. So let's solve that. I'm going to go to y equals, I'm going to put the model, I don't need to write 1 times, that just doesn't change anything. So in parentheses, 1 plus negative 0.0125 raised to the t power. There's my model. 1 unit decaying over time. I want to know how long will it take for that 1 unit to reach half a unit, 0.5 as a decimal. I need a viewing window where I can see that happen. How many days is that going to take? I don't know, but let me generate a table of values to investigate. I'm going to look at an every 10-day table of values. Going to the table, I can see that by the time we get to 60 days, we're below half a unit. So let's graph this on the interval from 0 to 60 days. Go to Window, set X-min equal to 0, set X-max equal to 60, and run zoom fit. The calculator will adjust the A-axis, the output axis, so that we can see what's going on that 60-day interval. Here we see the compound, the 1 unit of compounding decreasing at a decreasing rate. And here we can see its intersection point. That's where it hits. At that intersection point is where it hits 0.5 units. So let's calculate that. Calc, intersect, enter for first curve, enter for second curve, enter for guess. And that leads me to an intersection point of 55.10. T equals 55.10 days. That's my answer. So that's one calculation we can do, and that's the only calculation that was asked of us here. But I'm going to use this example to go over again some of these unit conversions, just so we have a little bit more practice, and you'll be prepared to do them for yourselves. So I'm going to clear this out. We're done with the question as asked. But let's answer some more questions. We know that we're going to look at some decay rates. The daily decay rate is equal to 1.25%. That's what we're given. Let's go to a smaller unit. Let's calculate let's see, let's calculate the hourly rate. There are 24 hours in a day, so every hour is 1/24 of a day. So what I need to do, this time I'm just going to do the calculations right here. I'm going to take the decay factor, the daily decay factor, which is 1 plus negative 0.0125. That's what I'm multiplying each day. If I want to know what happens in 1/24 of a day, I raise that daily decay factor to the 1/24 power, and that gives me the hourly decay factor. I can then subtract 1 from that and multiply by 100 to convert it to a percent. By the way, notice that R here that we just calculated is negative 5.24 times 10 to the minus 4. This is scientific notation, so that's a real small decay rate, hourly decay rate. I'm multiplying it by 100 to convert it to a percent. That gets me to negative 0.052%. Every hour, I'm starting with what I was given, the daily rate. Getting a daily growth, a daily decay factor from that, a daily base. And then I raise that to a number in days, but a week's worth of days. There are 7 days in a week. So that's going to be the number that I'm multiplying by every week on this exponential curve, the weekly decay factor. I subtract 1 from that to convert it to a growth rate. I multiply by 100 to convert it to a percent. And that gives me a weekly growth rate of negative 8.43%. Every week we're growing by negative 8.43%. That means my weekly decay rate, and that's what I'm going to write down. So now a weekly decay rate is positive 8.43%. Every week we're decaying by 8.43%. That compound is decaying by that amount. So those were some extra, no extra cost to you for that. I just wanted to go over those calculations again. That's how you move from one unit to another unit on an exponential curve. You always have to go through the base of the exponential function. For these problems, that base was a decay factor. You take the daily decay factor and convert that to a different unit and then extract the rate from that new decay factor. These are the calculations that we did to get the half-life that I started with.